This third tutorial will cover how to do basic FEA, finite element analysis, for stress in NX. So I'm going to use this link part that I made from the last tutorial and just do a simple axial stress test on it. So within NX, I'm going to go to File, and then I'm going to go to Advanced Simulation. And first thing I need to do is go up here under Context and create a new finite element model. That's what FEM stands for, and Simulation. So I'm going to click that. We'll wait a little bit. And I've got this dialog here. This creates the FEM finite element model in the simulation file. I don't think you generally need to change anything in here. You might if you need a different solver. This is just going to use Nastran. You can see the other options here. There's quite a few. A lot of these depend on what licenses you have. Nastran, it's a pretty good one to start with. You can see something about thermal and flow. I don't know exactly what flow it does. Really, this isn't CFD, so you need a completely different application, something like ANSYS Workbench to do CFD. But there's some options here. I know LS9 is for high nonlinear deformations like car crash testing and things like that, but I don't know what the licenses situation is for that. We'll just stick to Nastran. We're going to do, under analysis type, we're going to do structural. There's some axisymmetrics that you can do. If you're doing 3D shapes, though, you just want to use the structural. And the thermal as well. I've not done a thermal simulation, although that'd be pretty useful. I'm sure the approach works basically the same as the one for structural. It's just the boundary conditions and loads. They just are heat inputs and heat transfer, and it's probably the solution and mesh setup is similar. So after this tutorial, I might be able to play with that and get it working. And I might do one later on the thermal side, but we're doing structural for now. A 2D solid option, I don't need to do anything, so just none for that. So basically, you don't need to change any of this stuff. I'm just going to go ahead and click OK. Alright, so after I did that, this is the solution dialog, so I can name the solution if I need to. That's the solver that we just selected. Solution type, so if you open this up, there's tons of different solution types. The basic one is a linear statics global constraints. So this is for static simulations, as in the part's not accelerating, which assumes it's in equilibrium. So for that, if you have valid results from doing that, you basically have to solve out ahead of time what the boundary conditions would be for that to be correct, or you have to make assumptions on it. And it is a linear FEA, so small deformations and certainly nothing plastic deformation. If you think you're past yield or well past yield, this is not going to give anywhere near good results. Note there's lots of things in here, flexible body, buckling, nonlinear. So if you are going to have large deformations, nonlinear would be better than linear. It just takes a little bit longer to solve. It uses more of an iterative approach. It solves pretty quick, though. It's not that big of a deal. So if you are doing large deformations, you might use that. You can actually Google search these, and there's manuals for all of these available online, since Nastran is a pretty common solver. So you can just Google that exact phrase, and you'll find the whole PDF file is dozens, if not hundreds of pages describing what each one of these does, what the assumptions are. We're just going to do the simple linear statics, though. And in most FEAs, you can generally use that. I mean, most design cases, you're generally not wanting it to yield. There are some exceptions to that. So linear statics is generally, it's a good place to start, and it does most of the work. You can change some of the settings down here. I don't recommend doing any of this unless you know exactly what you're doing. So generally you don't have to. I'm just going to go ahead and click OK. And first step, so I've got my geometry that I've solid modeled. I need to make a finite element model. For a 3D part with this kind of configuration, I probably want to do a 3D tetrahedral mesh. For parts that are basically planes, a 2D mesh might work, or a series of planes or surfaces kind of patched together. That might work. 3D tet mesh is fine for this. So 3D tet mesh, it takes more resources because it does the elements go throughout the depth of the part. But for 3D parts, you kind of have to, because this shell doesn't really do that good of an approximation for them. So we'll just start with doing a 3D tetramesh. So I'm going to click 3D tetramesh. I need to click the body first. If you change any settings and then click the body, it goes back to the default settings, which is infuriating, but that's something NX does. So I've selected the body. I need to select element size. So what that means, so I'm going to go ahead and hit automatic element size, and I don't know where NX gets this automatic element size. Sometimes it makes sense, sometimes it's just absolutely crazy. It does 0.283, that's really coarse. So let me go ahead and apply that and just show you what that looks like. So it's going to take a little bit of time to mesh this. Obviously for larger, more complicated parts, this is going to take a lot more time. This is really simple. So you can see that mesh. I mean, it would probably work. The stress is somewhere in the middle of it would probably be okay, but up here around the bolt circle, I wouldn't trust that kind of mesh. But again, if you're just kind of interested, kind of a ballpark in the middle, you could try this, but you still probably want to try it at a little bit smaller mesh and see how the results change. I'll talk more about that later. So I'm going to use, I want to do 0.125. See, I forgot to click the body. So click the body, and then I'm going to change it to 0.125. I don't know why NX does that. That's really annoying, but there are some other settings here. So you can see that actually took very little time to do. So again, it's pretty simple geometry. I like that one. There's some settings here for element growth with volume. These are for basically, you see here the mesh is kind of fine. Here it's kind of coarse. You can change these settings and get different results for that. I haven't exactly got these things figured out yet. If I make them higher, let's see what happens. Yeah, you can see they grow a little bit more. This isn't really the geometry that you really have to worry about, though. But generally, I mean, if you have a mesh that's not as fine as you need it to here, I believe increasing these things actually increases the resolution there. So I kind of just do this by feel. I've done enough of these that I kind of know what a decent mesh looks like. But even then, you know, if you know what a decent mesh looks like, you still generally, once you run an FEA, you need to go back and half the mesh size, this element size, rerun it, and then double check your results to make sure that they don't change significantly between runs. But again, I'll talk about that a little bit later. So I like the that's 1/8 of an inch. I like that. I'll leave it since it's already meshed. I can just close that, and that's my finite element model. What I need to do now is apply loads to this, and this is one infuriating part of NX. 7.5, it was really bad. There wasn't an easy way to get back to applying loads. They actually made it a lot easier in 9. You just go activate simulation up here in context, and you can see you can switch back and forth between meshing and simulation. That button makes world much better. So use that to switch between meshing and applying loads. Okay, so if you'll note over here in the simulation navigator, I've got the solution created. I have load subcases here, and I have a load container, so I can apply different loads and then create subcases here and apply. So if I want to test different loading for the same part, instead of having a complete different model for that or a different file even, I just put a new subcase in there and a new solution for it, and in that new solution I put whatever subcase I want to test, and that way I can keep lots of things in the model without having to make different ones. Really nice organization. So again, just to keep things really basic though, I just want to put a simple axial load on this. So in order to do that, what I need to do is, so you might be tempted to just do a force and then the equal and opposite over here. Since this is a static simulation, even though those should, in theory and in most times in practice, cancel each other out and the thing will solve, sometimes that won't solve. So it's better to fix one side and then apply the constraint on the other side and then let the reaction forces solve themselves out over here. So what I mean by that is I'm going to basically fix this internal surface here and then apply a tension to this surface here. Alternatively, if you wanted to more accurately model a bolt being in there, you could use a bearing constraint, or you could just put the force on half that surface there. You can do that. You basically just have to split this surface, which you can do in the modeling process. I might cover that in a later tutorial too. But again, I'm keeping things basic, so I'm just going to apply the load to the whole bore. And that the loads right around, or the stresses right around that circle will be incorrect because of that, but in the middle they'll be pretty good. So what I want to do is go up here to constraint type. You can see all the different lists here. They correspond roughly to the various kinematic joints. So again, you really need to have an understanding of these kinematic joints before you start doing this. I want to do just a fixed constraint that basically welds all of the nodes which connect the elements in place, which means they can't move. I'm going to pick, so if I right click, you can see my selection filters. I can do these different things. So if you want to fix just the elements on a curve, or the nodes which makes the elements fixed on a curve, you can do that. That would be very not accurate for this simulation. So I want to do just do no filter, and then pick that face, and hit OK. And you see these little symbols. Basically, it takes all those nodes and it welds them to the ground. Now I want to apply an axial load down here. So I'm going to go up to load type. You can see all the different options you've got here. So all sorts of interesting stuff. You can see the temperature load if you're doing a thermal, and if you want to mess with a thermal. Hydrostatic nodes, a pressure if you've got a pressure, like if something is a pressure vessel, something like that. Torques, bearing, again, that's something that it might be useful for applying loads that are more realistic for things like bolts, or gears or cams or things like that work too. I just want to do a force though, again, keeping it simple. Magnitude and direction is what I want to do. Again, I'll just go pick this polygon face here. Just make sure it says polygon face so you're not clicking an edge. That would be bad. You can see all the options, including individual nodes, which another way, if you want to apply loads to very carefully apply loads to individual nodes, you can do that. I just want to do the face for now. So again, keeping it simple. And here's where I can put the force. Let's do 2,000 pounds. Expression. I do need to set a vector, so I'm going to click that. And I want to do in that, but I need to reverse it. Otherwise it'd be in compression, which would work. I could do it, but I want to do a tension test. So, okay. One thing I need to do before I go on is I need to set a material for this. It's kind of the main parameter you need for a linear FEA is pretty well just the modulus of elasticity. You actually don't need the stress, the yield stress for the material. You compare the results to the yield stress, but it's not something that actually goes into a linear one. So I do want to do manage materials. Actually, which one is it? It's not managed. Oh, I need to go into meshing. So I'm going to go ahead and close this. I'm going to switch back to activate meshing. Here is where I can manage material. That's not where it's to do it. Let's assign materials is what I'm looking for. Let me figure out where it's hidden. Sorry about that. I was close. It's under more here on my window. It might be on yours. It depends on how big of a screen you've got. It's assign materials is what I was looking for. So pick body. I want to do, let's just keep with the trend of using 6061. Apply. No errors. It's happy. Okay. So if you don't do that, the solver will complain. So now I've got a load over here, a constraint over here, a material, and a mesh. I should actually be able to solve this thing. So I want to go back to the simulation, and then I want to solve. And let's see what happens. So it puts this little solve dialog up. I just need to hit OK. And lots of stuff happens. So it calls basically a command line program for Nastran. I believe this is in Fortran. A lot of FEA code and CFD codes actually in Fortran. There are some performance advantages for that. I don't think so much nowadays, but there's still a lot of this code is in Nastran. So basically this stuff runs from a command line. So lots of stuff going on. What's interesting though is if you go to sparse matrix solver, you actually can see the equations being solved. In this case it's 37,700 equations. This is finished, so job finished. Obviously if you've got more elements, this is going to take longer. They use a very optimized sparse matrix solver to solve these things. It's just much better than anything you could write on your own, assuming you started and tried to write one of these on your own. And infinitely faster than you could ever do by hand. So that was done really quick. I just close it. There's this analysis job monitor. It's generally pretty useless, so I'm just going to cancel that. There's some information here, which it's not even, if you have an error, sometimes it's not even that helpful. But I'll go ahead and close that. So now I want to see the interesting results. So over here in solution, what I need to do is, there's results. I need to double click on results, and it's going to take me to the results viewer to show things something like the stress. So let me do so just elemental. If I expand that in the post-processing navigator, you can see all the different axes. So that would be the XX, ZZ, YY. Here's the shears. Those by themselves you really can't compare to something like the yield stress for the material. There's different models for doing that. This is again where you probably need a class like machine design before you actually cover this. But if you haven't, what you really, probably the best one to use to compare to yields is the von Mises stress. It takes these individual ones and it combines them together in something that is reasonable to compare to the yield stress. And when I do that, you can see the stress in the part. And notice, because these were all fixed and I applied the force over here, this is oval shaped. This is not oval shaped. So to get some kind of oval shapeness, I'd have to put constraints over here that more resemble the bolt. So over here, this is probably somewhat closer to what the stresses would look like in this. In the middle, it's just normal. It's what it's supposed to be. So you can see that's in the order of, you can compare to the scale over here, somewhere in the 4,000 pounds per square inch, which makes sense because this is an inch. It's a 1/4 inch thick, so you should get, that's a 1/2 inch. Let me think about this for a little second. Oh, I forgot, it's 2,000 pounds, so yeah, that makes sense. So it's a 1/2 inch cross section, 2,000 pounds, 1/2 inch. That should give me, divide 2,000 by a 1/2 inch, 1/2 square inch, I should say. That gives me the 4,000 pounds per square inch. So bring up von Mises. And so that's a pretty simple validation. This more interesting though is the stress around these. So again, around here is better than what I get up here because of the constraint. So in here I trust it. To do a better job around here, you'd have to apply the load the same fashion that it would actually be loaded as if there was a bolt in there. So a lot of the goodness of the results you get is how you apply the loads and your mesh size. So it'd be an interesting exercise after you do your assignment to run your FEA again with half the mesh size and just see how the results change around here. They shouldn't change that much in here. Around here they might change a little bit. And the hot spots here where it's up to 10 KSI, you can see where those show up there. Those might change a bit. I'm still not anywhere close. So this is 6061. This is 10,000 pounds per square inch is on the max end of that, compared to a yield. I think it's 40,000 pounds per square inch for 6061. So that's really not an issue at all for this. But if you did, if this was higher, if you needed a higher load and you're actually really worried about this thing failing like you are for almost all FEAs, then you are going to have to do a mesh sensitivity, cutting the mesh size in half, running this thing again, and seeing how things change, and trying to get your loads as closely correlated with how it would be loaded in the real world. If I want exact values here, it's kind of hard to compare colors here and here and get something that is accurate. So you can go up here to create graph. So in this on pass stress elemental, I can change these, of course. I can pick elements. I'll just pick several of them and then hit OK. And then I can put the graph in a new window, and that tells me values for the stress going across it. So that's something I could print out if needed. If you just want numbers instead of a graph, you could come to identify results and pick an element, and you can see what's going on in that element. Some of the other visualizations here, if I go to stress elemental nodal, it smooths these over the entire element using the stress at the nodes. So this is a little bit smoother profile. Again, though, how accurate this is depends on the mesh size, so you're still going to have to do a mesh sensitivity in it. But this tells you a little bit finer detail where the stresses are. Deformation too is of interest. So if I come up here to Displacement Nodal, I can get X, Y, Z. Magnitude's probably though what you're interested in. So you can see it's what is that? 2.4 thousandths of an inch deflection. Of course, it's fixed over here, so you're going to see the max deflection over here. So that's just the bare bones basics of doing a structural finite element analysis in X. You pretty well have enough to be dangerous right now, but it's something to play around with and just start using. It's really helpful when you're doing this to do common shapes, things like this, where you can validate your numbers and kind of build up confidence from there. There's shapes like this. I can check the stress in the middle of this. It's really easy to check it from the axial load in the cross-sectional area. So start with that and get comfortable with it. Once you start doing bigger, more complicated parts, you generally have to actually do testing with a universal testing machine or something like that to validate your process for going through it. So you can't just blindly trust the software, but this is something with a little bit of experience and a little bit of validation. You can get very, very accurate results and really save a lot of time. So that's it for this tutorial. I'll go ahead and stop it.